As you know, light comes in a lot of different types and colors. This covers an enormous range of wavelength, frequency, and energies. Where do these different photons come from? Electromagnetic waves can be generated by an accelerating electric charge. Recall a hydrogen atom. At the nucleus, you have a proton, and orbiting it is a small electron. Now, if the electron gets excited, energy is added to it, it can jump up to a different orbit. Now, this is a temporary effect when it jumps up here. So it's not going to be up here for long, which means when it wants to jump back down, it has to give off some sort of energy. So when it moves back down to its original ground state, to get rid of that energy, it has to emit a photon. So an electromagnetic energy allows it to drop back down to its comfortable ground state. Of course, there's lots of options for electrons to move up, and there's a lot of complicated rules that can explain how they can jump from one level to another level. And every atom is going to have different levels, and multiple electrons that can move around. This is why you can get all sorts of different colors, depending on the energy, the temperature, and the type of substance that's creating the light. If you energize or heat up a dense gas, you get a continuous spectrum like the rainbow. But if you have a low-density gas heated to the same temperature, thus the same energy, you get an emission spectrum. Essentially, this is because the lower density gas has less options for the electrons to shed energy or bounce energy around. Notice that there are only discrete lines, so each emission spectrum allows us to actually identify what element or molecule the light was created from. So, knowing what wavelengths the different colors are allows us to figure out what created the light. Thus, even if it's light years away, on the other side of the galaxy, we can figure out what an object is made out of. Of course, the light's not always traveling through a vacuum, which means it has the possibility of being absorbed on its way towards your eye or the instrument measuring it. For example, if you have a star out in space and it emits light and nothing's in between, your eyeball will see a continuous spectrum. But what happens if there's a cloud of hydrogen gas or some other element out in space? What would your eyeball see? Well, the light from the star would have to pass through the cloud. Along the way, all that hydrogen gas would start absorbing the particular wavelengths that it likes, leaving behind shadows in the continuous spectrum. This is called an absorption spectrum. That's because the gas cloud is actually absorbing those wavelengths of light. Notice how the lines of the emission spectrum and the absorption spectrum line up. So the thumbprint of what the gas was made out of, we can see. If you add these up to these ones, you would get the continuous spectrum. If you happen to be in the right place and could look at the cloud directly, what would you see? You would see an emission spectrum, which would allow you to identify the cloud as hydrogen gas. Of course, there's more to it. Here we see the emission spectrums for sodium, hydrogen, calcium, and mercury. Notice that they don't all add up to the continuous spectrum. Remember that a continuous spectrum needs to be a denser material, whereas emission spectrum only come from low-density gases. If the object is dense, like the sun, we see a whole bunch of dark spots, which are because the elements that the sun is made out of, those are the absorption spectra. Notice that different objects, when they are lit up because they're energized, peak at different wavelengths. So intensity tells you how bright it is. A Heine, which is a laser, is very narrow and really only just one wavelength. The sun peaks at a higher energy. Most of those colors are still there, they're just not as bright. Recall that the energy of a photon is equal to Planck's constant times the frequency. So the higher frequency light on the blue end of the spectrum has more energy. This means that if we can find the peak of the spectrum, we can figure out how hot an object is, even if it's out there in space. By measuring the color and wavelength of light, we'll be able to figure out what it's made out of, what it's blocking, and how hot it is. So this allows us to look out into the universe, figure out what something is, what type of energy it has, and possibly what's in between it and us.